Hi, I'm Ben-Yaakov. This presentation is entitled Deciphering C sub OSS of Power MOSFETs. Let's talk a little bit about the capacitances that we have, parasitic capacitances of a power MOSFET. We have capacitance actually between any two terminals. We have the gate, drain, and source of the transistor. Then we have between gate and drain the CGD, between the gate and source, and then we have between the drain and source CDS. So these are parasitic capacitances within the transistor itself. Now, manufacturers define parameters which relate to these capacitances in the following way. For example, there's a C sub ISS. SS means that these two are connected together. So this is the input capacitance when the drain and source are connected together. And this would be, as a matter of fact, CGS plus CGD. And then we have the C out SS, the output capacitance. This will be between drain and source when the gate is also connected to the source. This is the SS. And finally, there is the definition of the CRSS, which is basically the capacitance between the drain and the gate. Now, these are the definitions, but you'll find values for them in the datasheet. However, these are nonlinear capacitors. They are voltage dependent. That is, the value of these capacitors depend on the operating point of the transistor. And this is the main problem that we have, in that for any given voltage, the capacitance is different. There is a sort of a lot of confusion in this area. Now, we are going to talk in this presentation about the C out SS. This is the focus of this presentation. Let's see what's the important, or what are the effects of this output capacitance, and what is the importance of it. Now, consider a boost converter. We have an inductor, a diode, output section with a filter capacitor, and RL representing the load. This is the transistor switching on and off. There's a pulse going into the gate. When the transistor is on, that is, when there is a sort of a short or just a RDS on resistance, residual resistance between drain and source, current is flowing into the inductor, energy is charged in, and then during the off time, when this transistor is off, there is no connection here, like an open circuit, then this current is flowing through the diode to the output. So by turning on and off this transistor at a given duty cycle is defined as the ratio between the T on and the total time of the pulses, or T off, or duty cycle is between the off time and the total time. So by changing this duty cycle, you can control the output voltage. And as it turns out, for the boost converter, it's not important, but let me just point out, it's V out to V in is 1 over D off. Now let's see what happens during the turn on time. Before the turn on, the current is flowing through the diode. I'm talking about the continuous current mode, just a regular operation. Current is flowing through the inductor, diode, to the output. And now we turn the transistor on. There is a process going on. I'm not elaborating on it. Eventually, the voltage will start dropping down. So here we see it. Here is the transistor. While it was off, the voltage here was the voltage at this point. The diode was conducting, so this is basically V out. So this output capacitor is now charged to V out. As this transistor is turned on, all the energy of this capacitor is dumped into the transistor. This is a power loss. And the rate at which this energy is pumped in is the total power. That is, the higher the frequency, the higher the number of switching instances per second are higher and higher. There'll be more and more energy going into the transistor, and it could be significant. So this is the turn on instant and the effect of the output capacitor, or they turn on. During the turn off, however, we have a different story. Here is the transistor which is on, and now I'm turning it off. Here it is on, and I'm turning it off. While it was on, there was a current flowing. In fact, sort of following the gate drive, approximately. And now the gate is down, the current is down, and therefore the current of the inductor is now passing through this output capacitance. And there is a certain rate of rise here of the voltage, VDS, according to the VDT is I over C. The larger the C, the slower is the rate. Now this is good. This is beneficial. This is something we like because we don't want a overlap between the current and the voltage. And if the voltage would go very fast high, there might be some overlap with the current going down. So this is sort of beneficial. And of course, the rate here is a function of this capacitance. But the question is, which capacitance is this? Also, I didn't mention it. Let me go back for a second. The energy dumped into the capacitor, into the transistor, is the energy stored in the capacitor. If it would have been a linear capacitor, the energy is according to this equation, V squared C over 2. Well, in a nonlinear capacitor, this is not the correct equation. It's not. So there's an issue here. How do you get the actual energy? Because this is not the COSS simple expression that you'll find in graphs. So here are the graphs that manufacturers are providing. This is for a given IEEE power transistor. There's really no endorsement implied. This is just an example. There are many, many transistors, and all vendors will give you this type of information. So what we see here is CISS, this is the input capacitance, is a function of voltage. It's a nonlinear capacitor. This is in capacitance in picofarads, up to 100 picofarad, that's 100 nanofarad. And the one that we are interested in is COSS. Here it is. Starts here, very high value at the beginning, and then it tapers off, the capacitance tapers off, and there's a break here, and it goes like that. This is a logarithmic scale, so the changes are very large here, okay? So this is like, this is a decade. So from here to here, it's almost 2 decades, which means 100-fold. So it's a big change. Now, this capacitance is the so-called small signal capacitance. We'll talk about it in a minute. Let me just say that this is measured by perturbation at 1 megahertz. We see it's really highly nonlinear. And here is just an example. 1 point here. This is 25 volts approximately. And the value of this small signal capacitance is about 8.5 nanofarad. This is 1 nanofarad, 1000 picofarad, 1 nanofarad, 8.5 approximately from eyeballing here. And then we have the data sheet, the actual tables. This is again an IEEE. This is the same device. This is the catalog number. Again, this is just an example. And what we see here is the values CISS, COUTSS, and CRSS. Now, obviously, if these are single numbers, they are just for 1 point because these capacitors are functional voltage. So this is for 25 volt. Again, the excitation is 1 megahertz. Of course, VGS is 0, its transistor is off. And as we have seen, let me go back for a second, I found that for 25 volt, this is about 8.5, what I can say. And here it's 8.7 nanofarad. Okay, so this is just 1 point, which is kind of useless. I mean, what can you do with it? This is better set of information because you have it for any voltage, not just 25 volt. But then there are two more capacitances which are defined here, two parameters, two additional parameters. One is C sub O, it's hard to see, let me read it out. C sub O and parentheses ER, it's energy related. And then there is C sub O, output capacitance, TR, time related. One is 455 and one is 1930 gigafarad. Well, what are these? In order to understand it, we have to talk a little bit about nonlinear capacitors. So if you have a nonlinear capacitor, the very basic information on the capacitor is this curve. This is this long nonlinear curve, which is Q, the charge, as a function of voltage. This is the very basic description of the device. Now, once you have this curve, you can define quite a number of capacitances, and I'm showing here three, there are many more. One would be the total capacitance. That is, suppose the voltage is this value, this is now the charge, Q over V is capacitance, and this is the total capacitance. That's one definition. Then there is the local capacitance, or small signal capacitance, or the slope or derivative, and this is the slope at a given point, okay? dq over dv, this is this slope here. Obviously, this is a function of the voltage. Any given voltage on this curve will have a different slope. Same goes, by the way, for the total capacitance. All are voltage dependent. So this is another definition, and there is another definition here that I'm adding, which is a large scale, which means that suppose this is the operating point, and then the signal, the voltage is high, so you go on the curve this way. This will be delta Q here, and then delta Q over delta V is a definition of capacitance, and obviously this is also voltage dependent and different from all the others. So we have quite a number of capacitances here, and the one that the vendors are giving is this one. This is the local capacitance. This is the derivative here. Okay. So now, how do we measure these capacitances? The measurement is done under bias and with small signal. So for example, we have a bias, V bias, and we add to it some excitation. We are talking about C out SS, so these two are connected together, and we look here at this drain point, measuring voltage and current, and from which we can get the value of the capacitor. Or by a voltage source, this is capacitor, so the voltage here, DC, will be like here. This should be a very large resistor, so the impedance will be much larger than 1 omega C. Omega is related to this 1 megahertz, and then we again feed in a signal. This is the voltage. We measure the current, and from the current and voltage we can calculate the capacitance. So this will be a way to measure these local or derivative capacitance. Now we come to the question of energy. So power is V times I, and energy is the integral of P for a given time interval, which is the integral here. Now I itself is dq over dt, and V is Q over C. In this case, C is voltage dependent. So by these two, we can get this expression, which doesn't help much because this is a nonlinear expression, and also V is a function of Q. So it can be derived, but it's really cumbersome, and usually we won't go in this sort of analytical road to get this energy. If this would have been a linear capacitor, so this would be a constant, then of course when you integrate it, you get Q squared over 2, which turns out to be CV, the known expression for energy. This is incorrect when C is a function of voltage. Interesting, and I'm not going to elaborate on it. If you look at this curve, this Q as a function of V curve of this nonlinear capacitor, this area here can be shown. This area here is the energy stored when the voltage is this voltage, and this will be the charge. So this is, in fact, you have to get this area here. This is the energy. The way manufacturers are handling this issue of energy storage, actually there are two ways. One is to define an equivalent capacitor. The idea is that you can define an equivalent linear capacitor. This is a linear capacitor, see out, energy related, that when it is charged to the same voltage as the transistor, and this is correct for one voltage, and usually it will be for the maximum voltage, so-called VDSS, the maximum voltage permissible for the transistor. So this is a linear capacitor such that when the voltage on it will be the maximum voltage, the energy stored in it will be the same as the energy stored in the output of the power MOSFET transistor. So this will be, for one point, an equivalent capacitor. And if you know an equivalent capacitor, this is a linear capacitor, then you can go and use, of course, this equation. This will be the maximum voltage. This will be the equivalent capacitor, and get the energy. So this will be one way to handle it. Now, there is another issue here related to the rate of rise of the voltage during this transition from on to off, as we have seen before. So here, vendors are defining another equivalent capacitor. See out, time related. This is an equivalent capacitor that, when charged, and this will be by a current source, this is the equivalent capacitor, this is the transistor. When charged, it will reach the 80% or 0.8 of VDSS at the same time as the transistor. So this is the transistor which is charged by a certain current source. This is the equivalent capacitor, time related, and the intersect, that is the get to the same value, which is 0.8 of Vmax, intersect here at 0.8 of Vmax, and this is actually the definition of this capacitor. So this is this capacitor that will behave like that. So this is the time-related output capacitor. Why do you need it? Well, you can use it in order to estimate how long will it take for, or what will be the sort of average rise time of the transistor. Okay, you can approximate it by this rather than this. So here we have now the part of the table that we've seen before. Now we understand that there is a C out energy related. Here it is. And it's 455 picofarad. Again, this will be when the transistor is charged to the full maximum voltage, which for this transistor is 650 volts. And this energy stored in such a linear capacitor will be the same as the energy stored in the output capacitance of the transistor. And then we have this time-related, C out time-related, that is for the 0.8 of VDSS, the intersection with the actual behavior of the transistor at 0.8 of VDSS, and this is 1930. Well, that's a big difference between these two, obviously. There's different things, different beasts here. Well, let's have a look just for a second. What does this mean here? See, if this C out ER is 455 picofarad, charged to 650 volt, 455, the energy is 96 microjoule. So if you run this thing at a switching frequency of 100 kilohertz, so you have 100,000 times per second switching, then the power involved is 9.6 watts. that's 10 to the minus 6 and 10 to the fifth. So it's 10 to the minus 1 times 96, 9.6, almost 10 watts. That's quite a bit. So you lose 10%. This is hard switching, okay? We're talking about hard switching. That is that the energy from the capacitor is dumped into the transistor. In soft switching, there is some means that will actually discharge the capacitor without involving the transistor. And thereby you can save this power, part of it at least. So this will be the energy stored in this capacitor. And in fact, now vendors are now, in the last few years, are giving a better set of information related to this energy, and this is this curve. The equivalent, the energy related capacitor is just for 1 point. And obviously this is a little bit useless because you never operate a transistor at 650 volts, which is the maximum voltage. So now we have this curve, which is very nice because it gives you the energy. Now in energy units, well, forget about capacitances. This is just the energy stored in the transistor for any given voltage. And 650, it's about here, is about 100 microjoule. We found that it's 96, okay? So it's pretty much the same. And so for any given voltage, you get the energy stored. So you can, if you operate at 400 volt, then you can calculate it for 400 volt and the frequency you operate in. Now this is a nonlinear curve by itself, but it is representing a nonlinear capacitor. You see a break here, and the break here is due to the fact that, let's go back for a second here, see the C out SS has a break here, it's around 10, 20, 30 volts. This big break here exhibits itself in this curve. Here it is, this break here. In the next section, I'm going to cover the issue of SPICE simulation of nonlinear capacitors as it is related to the output capacitance of a power MOSFET transistor. Now, there is a paper that covers this issue, and also there is a video clip at YouTube, and I have this information printed on the page of this particular presentation. So if you look down below the title, you'll get this information, and in fact this is a link so you can go directly to this video clip. Now the simplest way to model a nonlinear capacitor is shown here. We have here two dependent sources. This is a current source. The nodes are labeled here C2 and C1, and this is a voltage source, and the output is here. It's a voltage, and this node is labeled C sub B. These are analog behavioral models. This is a G value, it's a current source, and the value of the current is a function of this expression. I'll talk about it in a second. And this one is an E table, which means that stored in here is a table. This is the table. These are X and Y values. And you can look at it this way. This expression here, which also belongs to this E table, is like the X value. And in this case, the X value is the voltage between C2 and C1. That is the voltage here. So for each voltage here, you get here a value. So if this voltage here is, say, 10 volts, the value is 1.1. This is, in fact, storing information, and SPICE knows also to interpolate between the points. That is, although these are discrete points, for SPICE it sort of becomes a smooth line, and any point in between, like 11 volts, is also permissible. So there is a voltage here. This is the X value, absolute value of this voltage. and it looks up this table and produces at this output this Y value, say for 10 volt, C sub B will be 1.1. So here we can store the capacitance behavior of a power MOSFET, the output capacitance, as a function of voltage. That is, let me go back now for a second. Here it is. We are talking about C out at S. Here, this is capacitance as a function of voltage. So each point here is XY. X is the voltage, Y is the capacitance. So this is the information stored in this table. Now we have this G value. This is the analog behavioral model, a current source, depending on this expression. This is a PSpice syntax that represent actually this equation. This is the state space equation of a capacitor. We have C, in this case C is a function of voltage, divided T, this is I, so this is the current. CV is this actually information from the table. Divided T, this is the operator of PSpice for a derivative. DDT is a derivative. So what we see here is the following. C sub green is taken from the table for any given voltage. There is a scaling factor because here you may not wish to put like micro or pico or nano, etc. Just put easy handling numbers, and therefore you might need to have a scaling factor like 10 to the minus 9 or something like that. And then you have the derivative of the voltage between C2 and C1. This is input voltage divided T. So this G value is actually implementing this equation while taking the value per any given voltage here from this table, which stores the information of this particular capacitor that we are working with. So this is a very basic, very simple model of a nonlinear capacitor implemented in PSpice. Let's see what we can do with it. So the first thing I did, I sort of digitized this thing. That's it, looking for XY. X is the voltage, Y is the capacitance. I picked up a few points and put them into the table that we just talked about, and then run a simulation which sort of mimics the way this capacitance is being measured. That is, injecting a small signal and looking at the capacitance by measuring the current and the voltage. And here I sort of reproduce this value for the purpose of seeing how well did I do. So you can see it's pretty good. To show the precision of this fitting, I'm going to put this one over this one, and here it is. And as you can see that, well, there are some missing points here. Well, I didn't do it too well here and here, but all in all, it's pretty good. So for our purpose, for this demonstration, I think it's okay. So what this thing is doing is verifying that the model that I have in PSpice is indeed fairly accurate as far as this COSS capacitance goes. Okay, now I have the model and I can do a lot of experiments by simulation for various things. For example, I can look for the relationship between the total charge and voltage. This is the Q as a function of V curve. Very nice. And we can see that this capacitor is really very highly nonlinear because the slope here is the capacitance, and there's a high slope here, which means high capacitance, and then it goes to be just about a constant capacitance here. And this is what we see, of course, with this derivative, that in this region it's pretty much this constant, the actual capacitance. This is sort of misleading here because this is a log-log scale. So up to here it's 100 volts, and from here to here it's 600 volts. So the span here is 600 volts, and here it's only 100 volts. So this is actually a small section. This is the largest section of the voltage. So going back to this, we see this behavior of this Q over V, but we can do much more. I can generate this energy curve that is the stored energy as a function of the voltage. To do that, I'll go back and use the very basic relationship. Let me look at it here. This very basic relationship of this integral. And I have, while doing simulation, I have the voltage of the capacitor, I have the current, and by integrating this, you can do it actually within PSpice, you can get just the energy. So you can feed it with any source, voltage or current source, and just look for the voltage times current, and then take the integral for any given point. And here is what we are getting, which is actually reproducing this curve that the vendor is giving, which means that he didn't do any mistakes, and apparently we didn't do any mistakes. Now we come to the question of the time dependence. So what I did here, I've taken, first of all, the MOSFET, the model of the output capacitance of the MOSFET, fed it with a current source, and then took this equivalent output capacitance, the time-related capacitance, and fed to it the same current. And here we see how the voltage developed as a function of time for the MOSFET and for this equivalent capacitance. And we see here the intersection at 520 volt. Now this is a 650 volt device. The intersection here is 520, and this is 80%. So this is a correct value for the equivalent time-related capacitance for the 80% of this device, which is 650 volt with the time-related equivalent capacitance of 1930 picofarad given in the datasheet. However, there's a point here that perhaps should be cleared out. This thing is correct when the charging is with a current source. If the charging of the transistor or the equivalent capacitor is by a voltage source with a resistor, RC type circuit, and this will be this case. This is the current source, and this is this case. In this case, the intersection is at a different point. So this is the wrong value of the equivalent capacitance time related for this case. This is actually not too bad, and we can sort of tolerate it because in actual power conversion circuits, many times the charge are by sort of a current source. A large inductor with a current in it is like a current source. So this is pretty good and a pretty good approximation of this thing. Now, of course, if you have a SPICE model, you can test any case, any situation as you wish. So this actually brings me to the end of this presentation. I thank you very much for your attention. I hope you have found it interesting and it will be useful to you in the future. Thank you very much.